In this video, I show how to evaluate definite integrals involving sine and cosine by using the polar representation of complex numbers and then applying the residue theorem. I discuss one example to evaluate using the Cauchy's residue theorem and also evaluate the same integral by the usual method discussed in calculus 2. So the first method is using the Cauchy's residue theorem. We would like to evaluate integrals of the type integral 0 to 2 pi, a function of sine theta, cosine theta, d theta. Let's take an example here. We would like to prove integral negative pi to positive pi 1 by 1 plus sine squared theta d theta to be square root 2 times pi, or we would like to prove that as 4.4429. Now, in order to evaluate this, we would like to use the method 1 using complex integration. For that, let us take this given integral negative pi to positive pi 1 by 1 plus sine squared theta d theta. That is nothing but 0 to 2 pi 1 by 1 plus sine squared theta d theta, because it is integral negative pi to 0 plus 0 to pi. Negative pi to 0 is the same as 0 to pi. So you have integral 0 to 2 pi 1 by 1 plus sine squared theta d theta. Now, let us take the unit circle C mod z equal to 1, where z equal to e raised to I theta, theta ranging from 0 to 2 pi. So you have a closed circle here with center at 0 and radius equal to 1. So if mod z equal to 1, we know that z is equal to 1 into e raised to I theta. So using Cauchy's residue theorem, we would like to convert this integral 0 to 2 pi 1 by 1 plus sine squared d theta as integral over this c. The c is the unit circle, f of z dz, but f of z is my function which is converted into z. That integral function 1 by 1 plus sine squared theta d theta must be written in terms of c now. And you can say that this is 2 pi I s of ci using Cauchy's residue theorem, where SFCI is the sum of the residues of the function inside this particular unit circle C, mod z equal to 1. Now, in order to show the first method, I have included a handout. So we are trying to make use of the polar form of it. So when z is e raised to I theta, which is cosine theta plus I sine theta, we know that sine theta can be written as 1 by 2i times z minus 1 by z. So sine squared theta in our case will be negative 1 by 4z squared, z squared minus 1 the whole squared, and also d theta becomes dz by iz, because e raised to iz, I theta is z. So by differentiating that, we can prove d theta is dz by iz. So since it is taken as integral over c, d theta is dz by iz by 1 plus whatever sine value we have, we can include that. And we can simplify this as 4 by I integral over c z dz divided by negative z raised to 4 plus 6z squared minus 1, where this z by negative z to the 4 plus 6z squared plus 1 is my function f of z. So this is 4 by I 2 pi I into s of ci, which is negative 8 pi s f ci. So now I would like to find what is my s of ci. In order to find s of ci, we take the function f of z which is z by, if I'm pulling that negative sign outside, it becomes z to the 4 minus 6z squared plus 1 in the denominator. The poles of this function are at which the denominator is 0. That is z to the 4 minus 6z squared plus 1 equal to 0. Poles are the points at which the function is not analytic. So it is not analytic when the denominator is 0. Equating the denominator to 0, I can find two values for z squared because it is a fourth degree equation. So I can find the value for z squared, which is 3 plus or minus 2 root 2. If I take the roots as alpha and beta, then the roots of this denominator z to the 4, your z will be plus or minus root alpha and plus or minus root beta. So if I take plus or minus root beta, only that root beta will lie inside the contour C. That is plus or minus square root of 3 minus 2 root 2 will lie inside C. So the residue of the function, since it is a simple pole, both plus 3 minus 2 root 2 and minus root of 3 minus 2 root 2 both will lie inside C. Whereas this plus or minus alpha, because 3 plus 2 root 2 will be greater than 1, when you take square root of that, whether it is positive or negative, those points will lie outside. So we are not worried about alpha, we are worried about beta, square root of beta, plus root beta and negative square root beta. You can find the residue of the function at plus square root beta. Since it is a simple pole, it is limit z tending to square root beta, z minus square root of beta into f of z. F of z can be written as z divided by the denominator as z squared beta minus beta times z squared minus alpha. We can retain the z squared minus alpha, but z squared minus beta can be split into two factors, z minus root 2 beta and z plus root 2 beta. You can cancel out z minus root 2 beta, so your answer will be negative 1 by 8 root 2 when the limit z tends to root beta. We get the result as negative 1 by 8 root 2. The same way, we have to find the residue of the function at z equal to negative root beta. To get that, let us take the function f of z at z equal to negative root beta the same way like what we did in the previous case for root b. We have to find the limit at z equal to negative root b. It is also a simple pole. So using the formula of residues, we get the result as 1 by 8 root 2. So SFCI is the sum of the residues, which are the sum of the residues of the function at z equal to root beta and z equal to negative root beta. Adding them together, we get that as negative 1 by 4 root 2, or integral negative pi to positive pi d theta by 1 plus sine squared theta. Substituting in my previous result 1, which is negative 8 pi SFCI. My SFCI is negative 1 by 4 root 2. Simplifying this, we get the result as root 2 pi. So using Cauchy's Residue Theorem, we got the value for integral negative pi to positive pi d theta by 1 plus sine squared theta to be root 2 pi. Let's see another method which we have already done in calculus 2. So the usual integration what we have learnt in calculus 2 can also be used. So in method 2, I have the integrand 1 by 1 plus sine squared x dx. I divide both the numerator and the denominator by sine squared x. When I divide both the numerator and denominator by cosine squared x, 1 by cosine squared x, 1 by cosine squared x plus sine squared by cosine squared x. We know that 1 by cosine is secant, so it is secant squared x by secant squared. Sine by cosine is tan, so it is tan squared. We also know this identity, 1 plus tan squared is secant squared x. So the denominator becomes secant squared x plus tan squared, which is 1 plus 2 tan squared x. And if we take a substitution u equal to tan x, your du becomes secant squared dx. So this whole integral, which is in terms of x, can be converted into an integral in terms of u as du by 1 plus 2u squared, because you get 1 plus 2 tan squared, which is 1 plus 2u squared, which is nothing but du divided by 1 plus root 2u the whole square. Again, if I take a substitution for root 2 times u as y, my dy is root 2 du. So this whole integral can be 1 by root 2 tan inverse of y. But what is my y? Y is root 2 u and my u is tan x. So it is 1 by root 2 tan inverse of this y is root 2 times tan x between the limits negative pi to positive pi. When I plug in the upper limit, pi, we know that tan pi is 0 and also tan inverse of 0 is pi. So here in the upper limit it becomes 0 and also tan inverse of negative theta is negative tan theta. So taking this tan of negative pi as negative of tan pi, I get a positive sign here. Again, I get tan pi to be 0. So this will be tan inverse of 0 plus tan inverse of 0, which is pi plus pi, 2 pi by root 2 or root 2 pi. So this is the value what I get using the calculus 2 method. But in many ways, the residue theorem makes life a lot more simple by allowing the evaluation of integrals that otherwise be difficult to complete using the techniques we learned in calculus 2. But for this particular problem, I think the calculus 2 method is easier, but in many cases, the residue theorem makes our life easier. So in this video, I was trying to explain how to make use of the Cauchys Residue Theorem to evaluate integrals of the type integral 0 to 2 pi, a function of sine theta, cosine theta, d theta. We took one example. We showed two different methods using the Cauchys Residue Theorem and the usual technique what we learned in calculus 2. Hope this video was helpful and hope you enjoyed watching this. Thank you for listening and thank you for watching.